Hello and welcome to this chemistry video. We've been following Brown, LeMay, Burston, and Murphy's chemistry, the central science. We are in chapter 4 on aqueous, liquidy solutions and things that happen in them. And this video is on concentrations of solutions. Now, we all understand the idea of concentration. You may not have known to call it that. And I don't mean concentration or the board game concentration. I mean liquidy concentration. Basically, concentration is the ratio of liquidy stuff in liquidy stuff. Solvent, the ratio of solvent in solution. Now that may sound, what? Well, let me give you an example. Well, I just made a coffee a minute ago. Have some lovely K-cups. K-cups have, the company, Starbucks, has already put exactly the right amount of grounds in it for it to come out just right. But in the old days, when I was a young man, you had to scoop coffee grounds into a coffee maker. And I always found that in the honor of God the Father, Son, and Holy Spirit, 3 scoops was just the right amount of coffee scoops to make just the right concentration of coffee. Now, if you're an old coffee drinker, you know that sometimes, oh, this coffee's so strong, I can hardly stand it. Sometimes they used to say that truck stop coffee was way too strong. On the other hand, sometimes I've had coffee that's just, it's almost like, this is like water. I mean, why even drink it? Throw it out, start over. Or maybe you've had tea that's too weak, or something that you don't is just too weak. Maybe somebody watered down grape juice concentrate and they put too much water in it, or you drank it without watering it down. Oh, I guess you're supposed to dilute this. And we kind of understand this sense of concentration. If you don't understand it now, you will soon enough next time you encounter this kind of a situation. The main concept of this section is molarity. Molarity is basically a unit of concentration that is the number of moles per liter of something. Now, you don't have to have a whole liter of something to have the concept of molarity. Like 1 mole of something in 1 liter is a 1 molar solution, but a half a mole in a half a liter is also a 1 mole solution, or 2 moles in 2 liters is a 1 molar solution. It's all about the ratio, divide by divide, that the molarity comes into play. So a 1 molar substance, or a 1 molar solution, that is a solution that has the ratio of 1 mole for every liter of concentration. So here's an example. In honor of my son Tom and my daughter Sophie, who like the master of disguise, we're going to do add the copper sulfate. Anyway, let's say that we have 160 grams of copper sulfate dissolved in a liter of solution. Well, I picked this number because the molecular weight of copper sulfate is 160 grams per mole. I went to the periodic table and I added up the atomic weight of copper plus the atomic weight of sulfur plus the atomic weight of oxygen times 4, and it comes out to just a smidge less than 160. I won't go into how they pick the ratios in the atomic in the periodic table. That's a previous video. But anyway, so let's say we've got 160 grams of it. That is, wow, I picked the numbers so they would be easy. 160 divided by 160, that's 1 mole. Grams divided by grams per mole, grams cancel out and you're left with moles. So that's 1 mole of copper sulfate in 1 liter per 1 liter, or in 1 liter for this example. That's a 1 molar solution of copper sulfate. Not that hard, really. 1 mole per liter, that's a mole. What about with ions? What about with electrolytes? Let's say you have a 1 molar solution of sodium sulfate, right? So how many, what's the molar, this dissolves in water. So what would be, if you have a 1 molar solution of sodium sulfate, what's the molarity of the sodium ion and what's the molarity of the sulfate ion? Well, the answer is, for every 1 molar solution of sodium sulfate, that will be a 2 molar solution of sodium ion and a 1 molar solution of sulfate ion. You can see how this works, right? Because the subscript of sodium, you have 2 sodiums for every molecule of of sodium sulfate, right? So you got to multiply the molarity because you're going to have 2 moles of sodium for every 1 mole of sodium sulfate. And so that means a 1 molar solution of sodium sulfate will have 2 moles per liter of sodium ion. Now, the 4, don't let the 4 throw you off because that's a unit. SO4 is a unit. It's 1 unit of sulfate. And so there's only 1 unit of sulfate for every 1 unit of sodium sulfate. So it's going to have the same molarity. 1 molar solution of sodium sulfate will have a 1 molar solution of sulfate ion in it. Basically, the electrolyte concentration is the molarity of the overall compound, like 1 molar here, times the subscript in the formula. So because the sodium has a 2 subscript, we're going to multiply its molarity times 2. Because the sulfate is 1 unit, it gets multiplied by 1. Okay, so that's how you figure out the molarity of an ion in a solution given the molarity of the overall compound. Okay, a lot of this is the common sense back in chapter 1 of knowing how to cancel things out, right? So if you want to find moles, you take the molarity and you multiply it by the volume. And liters times per liter cancel out and we're left with moles, right? So it's just the kind of common sense. You don't have to necessarily memorize all the formulas. You just have to know how to cancel out the labels, so to speak. Now, you will often in practice have to dilute things. So for example, in a moment, I'll mention that hydrochloric acid usually comes as a stock solution at 12 molar solution. So it's 12 moles per liter. Well, what you need to change that to get it to where you need it to go for your experiment, right? You've got to dilute it. We all understand the idea of diluting something. So here's a nice little formula. The moles before and after dilution are going to be the same, right? The number of moles of copper sulfate or whatever before are going to be the same as the number of moles after, even though the concentration has changed. And so using this dimensional analysis thing, so the molarity of the concentrated solution times the volume of the concentrated solution is going to be the same as the molarity of the diluted solution times the volume of the diluted solution. This makes sense. Why? Because molar is, for example, moles per liter. Volume is, for example, liters. And we've just seen that moles per liter times liters cancels out and you get moles. So when you multiply the molarity of the concentrated solution times the volume of the concentrated solution, you're going to get the number of moles. And that's going to be the same before and after you dilute it. And so if you take the molarity of the diluted solution and you multiply it times the volume of the diluted solution, that's going to give you moles as well. So moles equals moles, it's going to be the same. And by the way, you don't have to do this in per liter, for example. As long as you're consistent throughout, you could do milliliters, you could do something, so you could do gallons if you knew the molarity in gallons. But the key is that you be consistent with the volume throughout, all the way throughout. But it will work for other units other than just liters. A couple of practical items as we finish this up. Sometimes, you often will want to dilute a acid or a base. They helpfully suggest in a footnote that you don't start by adding the water to the acid or the base, because there'll be that kind of heated reaction that will cause splattering and you might burn yourself. So always start when you're diluting an acid or a base by adding water to the acid or the base to get it a little bit more diluted, and then you can take it the rest of the way. So always add the acid to water, not the water to the acid when you're starting off. And then I already mentioned this, hydrochloric acid usually comes as a stock solution of 12 molar solution, 12 moles per liter of hydrochloric acid, and you've got to delete it from there. Well, this has been a video on concentrations of solutions.